Good afternoon, 44Con. I'm James. I'm here, unsurprisingly, to talk about Windows 10, as the name suggests. Quick bit of background. You've got to have an obligatory background side, of course. I work for Google on the Project Zero security research team, and I specialize mainly in Windows work, Windows research, on the local privilege escalation side primarily. And I'm very much logical bug focused. I don't tend to do fuzzing unless I really have to. Always, I try and find interesting bugs which are sort of design flaws or sort of logical bypasses of code. So what am I actually going to be talking about? Because obviously the title is a bit, I suppose, passive-aggressive almost. So I've been doing some research on some of the insider previews of Windows 10, and obviously now Windows 10 is now available to the public, and people can download it and install it. And obviously I was looking for interesting new security features, but also new security flaws, as you would do. And Windows 10, I think, for the most part, is kind of awesome for security. A lot of effort seems to have been going into Windows 10 to make it even more secure. Windows 8 was already sort of like a shift of sort of thinking of how to secure Windows, and Windows 10 sort of takes that further. But of course, with any large piece of complex software, not everything is perfect, and so there's obviously some regressions in some functionality or sort of stupid, like, why is that even still there sort of thing. So as I've already pointed out, I'm a logical, local privilege escalation kind of guy. I'm very much looking at Windows 10 from that sort of perspective. I'm not looking at it from a sort of remote attack perspective. So if you haven't actually seen Windows 10 yet, which I'd be surprised you haven't at least seen something about Windows 10, it looks more or less like that. I would love to know how much money they actually spent on the awesome T-Rex with the Ninja Cat, because that is great. I really want a T-shirt, but obviously they haven't given me one yet, which is a shame. And yeah, you can get it. They've been pushing it quite heavily, so obviously you can choose if you're using Windows 7 and above to install Windows 10. Even helpfully, they'll automatically download it for you and install 6 gig of data on your hard drive, because obviously why not? Because they want you, Microsoft wants you to have Windows 10 really, really badly. So this is sort of like a slide which you would find pretty much in any sort of Windows privilege escalation talk. And this is sort of like what we consider to be a sort of a local attack surface for Windows, from a sort of perspective of an attacker, where an attacker wants to jump between privilege levels. So anything which is sort of like a horizontal level could be arguably considered a security boundary. So this is a place where if you can hop over that boundary, it is a security bug which Microsoft presumably will try and fix. The interesting thing here is that actually sandboxing is now sort of pretty much considered to be a security boundary as well, which surprised me somewhat. So effectively, like, as an attacker, you've probably got in as a sandbox into, say, a sandbox through the web browser, or you're at a user level, and you want to gain sort of higher privileges. So you want to sort of jump into local system, or you want to get into the kernel and compromise the entire machine. And so obviously from a local privilege escalation, those are the sort of places we want to look. Now it's worth pointing out that Microsoft are doing their bit for op-free calc, if you've seen the posters around, because basically now you no longer have to kill a copy of calc.exe whenever you do a local system escalation, because if you try and run calculator at local system, you get this dialog. Basically, it won't pop calc at all. It will say you need some other application to run calculator. So I think they deserve like a round of applause for their sort of like helping to free calc from its poor position in life. So I thought I would actually sort of look in a general sense on attack surface. Is Windows 10 attack surface better or worse than previous versions of Windows? And the obvious one to look for is anything which was sort of in those top two tiers of my attack surface diagram. So basically system services and kernel drivers. So what I felt was the best immediate metric I could choose, well, let's just look at how many system services and system drivers are actually installed on Windows 10. But in isolation, that's not actually a very useful metric because you have no way of comparing it to anything else. So I did the same for 7 and 8. So I installed a default installation of 7, 8.1 update 1, and 10 on the same sort of VM implementation, updated them to the absolute latest I could, and then just did a simple measure of how many system services and system drivers are installed by default. And in this case, blue represents system services, and red represents drivers. And I think you could probably clearly see a definite upwards trend since Windows 7 to Windows 10 in terms of the quantity of drivers. And theoretically, this has some sort of reflection on the maximum attack surface which could be available to an attacker from a local privilege escalation perspective. But of course, that's not really an accurate metric because that's not necessarily representative of the real attack surface of the platform. Another useful metric you perhaps want to find out is actually, just because I can break into a system service, what sort of privilege would I get? Would I actually compromise the entire system doing so? Or would I actually only get sort of a relatively low-level permission? So this is my next diagram, and this basically just charts the privilege levels of these system services. Because obviously a driver has kernel privileges. It's already God, so you don't need to measure that. But these are the services. And so this is basically a graph of the percentage of a particular type of user account which a service runs at relative to the total number of services. So Windows has 3 main built-in service accounts. It has local system, which is effectively local administrator, local God account. You have network service and local service. And network service and local service, for all intents and purposes, are more or less the same from a security perspective. Local system gives you administrator rights. Network service or local service does not. It does not give you direct administrator rights. You may be able to break out of that once you're at that level, but it doesn't actually just immediately compromise the system. Now, in this diagram, blue represents local system. And hopefully you should see that there seems to be an upward trend in local system services as a percentage of the total number of services between 7, 8, and 10. And of course, this is not just a higher percentage of local system services. You have to remember that there's more services. So as an absolute measure, there's considerably more services running a local system than there was on 7. And that doesn't sound quite right. But of course, sometimes things surprise you. So it turns out I was playing around with Windows 10, and I saw this in Process Explorer. Okay, that's a bit odd. SVC host running as normal user. That's a very strange thing to see. You only sort of see that with malware and that sort of stuff where they're pretending to be SVC host. They're not actually SVC host. So I thought that's very odd. But it turns out it is actually a Windows 10 feature. You can register a service as a user-level service, and it will spawn a copy of SVC host as a normal user account. Oh. So if you see that, it may be malware, it may not be. Who knows? Oops. Okay. Yeah. Okay. So as a measure of attack surface, we now know that Windows 10, by default, seems to have more services, and more of those services are running at the highest privilege account you can get. Okay. But of course, services can be turned on and off. Not all services which are installed by default are running at any one time. So you kind of want to make an assessment of the actual real running attack surface on Windows 10. So the way you kind of do that is you look at the start mode of that service. And a service can have a particular start mode, and it's usually it's split into 4 main groups. You have the automatic start mode. These are services which will automatically start when you boot your machine. Now you have manual start mode. And manual start mode is a bit of a misnomer. Yes, it can be just an administrator has to come along and say, start this service. But it could also be in response to certain actions. For example, if you have a COM registration, which registers to a local service, it may actually start a service for you in response to trying to access a local COM object. Now, something that was introduced in Windows 7 is something called the triggered services. And these are services which effectively are manually registered. but there's some sort of information relating to that service which says, if this action happens, for example, if the network comes up, or I get a particular event tracing for Windows event sent to me, bring this service up. So these are effectively services which, while technically manually started, can be started automatically, usually from any privilege level. So you could almost consider them to be attack surface as well. So in combination, you can kind of see there's not much of a difference, to be fair, but actually like triggered services have grown massively since 7. And so the number of services which could theoretically be running under control of the user has also increased. So not only have we got more services, we've got more privileged services, and potentially more services which could actually be running at a higher privilege which you can attack, which is always good from a local attacker perspective. Now, I don't want to completely forget about drivers, because obviously drivers are kind of important. And I struggled a bit to sort of work out a good way of measuring this, because obviously drivers are potentially a slightly different model to system services. There's no reason to believe that, Microsoft can register thousands of drivers on your system if you like, but these drivers may only come up in response to a particular piece of hardware or particular condition which actually arises, which requires that driver to be loaded. So by default, they may not actually be vulnerable unless someone has a particularly obscure, weird USB device or something like that. So I just did a basic measure of device objects. So device objects are user-accessible device nodes, effectively like /dev in a Unix system, which basically allow you to connect and send commands to that device driver. And these are figures taken from just the normal user. So these are not an administrator user. These are just like your normal, everyday, standard user. And actually, it's good that basically it's gone down over time, it seems. 7 was higher considerably than 8, and then 10 is subtly, slightly less than 8. So in terms of drivers, direct attack surface, maybe less. Although potentially other drivers have been consolidated into one or something like that, who knows? But this is just sort of throwaway statistics. It's just to give you sort of a measure of what is actually happening. Now, certainly, one thing which, if you have a look around the literature of Windows 10, watch some Channel 9 videos on this, one of the things which sounds really, really interesting is something called isolated user mode or virtual secure mode, depending on what people are calling it at the time. And this is basically a mechanism to allow you to almost run 2 copies of Windows, one sort of secure and one non-secure. I think I'm not doing it describing it like that. As I say, if you want to get a bit more information about actually what it's doing, there's some Channel 9 videos which are quite good at actually giving you information about that. But the interesting thing is, what it allows it to do is separate out some user mode code from other user mode code, even if you were able to compromise the Windows kernel itself. And that's kind of an interesting feature. And then any communication between, say, user mode and isolated user mode are over some sort of prescribed RPC channel, which obviously is then a narrow barrier which you can perhaps contain more easily and more easily assess. So is this actually used for anything of any use? Well, about the only thing it's currently used for, as far as I am aware, is isolated LSASS. So LSASS is the process responsible for actually sort of doing authentication. If you're on a domain, it may get your Kerberos tickets, all that sort of stuff. But it's also the key weakness pretty much in the Windows domain architecture relative to a local attacker being able to get your credentials. Almost certainly there'll be some people in here who do infrastructure tests. They will have got themselves on a machine somewhere, run Mimikatz, dumps the current domain admin's password or hashes, and you can then replay them and get access to the entire domain and compromise the domain. So isolated LSASS actually provides a mechanism to firewall that off from effectively other user mode and even other kernel code and protect those credentials and stop them being compromised. But unfortunately, from a sort of consumer perspective, it's actually utterly useless because as far as I'm aware, isolated user mode is only available in enterprise. So even if you are a relatively small company which they buy in a Windows server, Windows 10 everywhere, Windows 10 Pro everywhere, you can't deploy this mitigation in your environment because it's enterprise only. And you can't use it to do any of your own stuff. You can't come up with like a really awesome new feature which you may want to use, and like this isolated user mode would provide that functionality because probably for good reason, you can't just run arbitrary code in there because otherwise malware would probably run arbitrary code in there. So it's a very restrictive use case. Now, I said I wouldn't really talk about remote attacks, and I'm trying to stick to that. The browser in this case is a bit of a special case for me because of sandboxing mechanisms, basically. So Edge is the new hotness from a browser perspective for Windows 10. And it's basically based on, as far as I'm aware, Microsoft have taken the Trident rendering engine from IE and tried to gut it, tried to remove all the crap, all the legacy rubbish which didn't need to be there, and try and make it super secure and reliable. And so things like ActiveX is effectively gone. It's not strictly true in a complete sense, but it is, from a varying perspective, it is gone. But obviously, from my perspective, the app container sandbox is always on. So IE11 or IE10 had enhanced protective mode on Windows 8 and above, but it was never enabled by default, except for like a 1-month window when 8.1 came out. And there was too much compatibility issues, so it was reset in protective mode. And protective mode is effectively worthless. It's not completely worthless, but it more or less may as well be. So it's great that actually Edge has this by default, and it's now a securable boundary so that if you can find an escape out of app container, then that's something that Microsoft, in theory, will fix. But nothing's ever perfect. Obviously, I can't really throw stones here from a Google perspective, but it's sad to see that, obviously, Flash just continues to keep on going and keep being a useful primitive to exploit even the latest, greatest browser which comes out. Oh, well, we have to have Flash because some advert needs it. But of course, in IE's case, or in Edge's case, it's still using the ActiveX version of Flash. And the trouble with that is it increases the attack surface of the platform because there's been numerous occasions where, for example, a Word document has hosted Flash. Because it's an ActiveX control, it can be hosted in any OLE container. So Microsoft have unfortunately had to have deployed like Flash, and they couldn't just keep it to Edge. It has to end up running in IE and all the other OLE containers, which kind of sucks. And it turns out like some of the things which web browsers have been securing against after people have realized, hey, that's a really stupid thing for you to be doing, things like protocol handlers. If you use your mobile phone, like your iPhone or your Android phone, if you click on a link, it may end up dropping you into the store so you can buy some crappy app. And that usually is through some sort of protocol handler or URI handler. But of course, presumably for the ability to spawn the Windows store so you can also get some crappy app, if that crappy app even exists, it supports the ability to navigate to protocol handlers without even prompting you as to whether you want to navigate to that protocol handler. So the classic example is there's a calculator : protocol handler, which obviously kills a calc.exe every single time it runs. Terrible. And that will run with no prompts. You can just navigate to calculator : and it will work. Ridiculous. So it's certainly something worth looking at. And of course, like all this effort spent trying to rip out all the crap, and then people post, oh, here's a memory corruption, and there's fixes for Edge this month for RTE vulnerabilities. And yes, there is a lot of underlying changes going on under the hood which try and mitigate against these sort of vulnerabilities. But the fact that you can just find a memory corruption or a crash relatively easily is kind of not great from a security perspective. Now, one of the things I hit far too often in my dealings with Microsoft, and usually when I'm looking at local privilege escalation stuff, is user account control. And I would say it angers me somewhat, like to a degree, like the way in which it's it's treated sometimes. So I'm sure pretty much everyone has seen user account control if they've ever used a Windows machine since Vista. They will have seen this prompt or a similar prompt. And how could you not click yes to Honest Joe? He's clearly trustworthy, and it's not malware, honest. So the strange thing about UAC bypasses, so basically if I can bypass that dialog box, is if I give them to Microsoft, invariably, if they are considered to be UAC bypasses, it's kind of it's not a security boundary. We're not going to fix them. Okay, fair enough. But we might fix them in the next version of Windows. And it turns out a couple of my bugs, which weren't going to be fixed in 8, they'll fix it in 10, it's fine. They'll never backport it, but they'll be fixed in 10. Awesome. So I thought I'd at least go through one of these and show you the sort of, because it's kind of an interesting bug. Nothing really like to do with like the sort of Windows 10 specific. It doesn't even work on Windows 10 because they fixed it. But I thought I'd at least go through the bug because it's kind of interesting. So you may know about sort of auto-elevating applications in UAC. Since Windows 7, to try and reduce the number of prompts, there's actually like an auto-elevation mechanism. And so if a particular signed Microsoft binary has a particular manifest field, it will automatically run as the administrator without actually prompting the user. But it actually goes back to Vista. So Vista had something called UI access applications. And UI access applications, they don't give you administrator privileges, but they increase your integrity level. And so it potentially increases your ability to attack other windows which are sitting on the same desktop. But that's just sort of based on signing. So it's based on signing, based on a manifest condition. So obviously the developers wanted to make sure that you couldn't just run an arbitrary UI access application from anywhere you like, just sign it and it works. So they required, whenever the system service which is responsible for instantiating this process, it is required to be in a secure location. And the definition of a secure location is actually sort of hard-coded into the service. But for example, in this case, if you're under C Windows is secure. And if you can put a file there, you get auto-elevation. However, if you put it under C Windows tracing, that is not a secure location, and therefore it is banned. That seems fair enough. But why like, surely Windows itself is secure. Everything is secure in the Windows, you'd assume. Well, it's actually not. You only have to look at the security permissions of the tracing directory relative to the Windows directory, and you'll see the problem. The Windows directory is ACLed so that a normal user cannot write new files to that directory. On the other hand, the tracing directory, a normal user can just arbitrarily insert files into that directory. So it's clearly insecure. You can't treat that as secure. But that got me thinking, okay, how can I write to the C drive without, how can I write to the C Windows folder without writing to the C Windows folder? Because all the service was doing is looking for the last backslash, or last forward slash, whichever one, chopping that off and saying, right, that's the directory path. So obviously in our case, malicious.exe, if it was under Windows, would be under Windows. Is there a way of getting a file in Windows which isn't really in Windows and bypassing our DACL? And it turns out, yes, there is. Because we can use alternate data streams. And alternate data streams, for whatever insane reason, are allowed to be created on directories. And they're not like an alternate directory, they're actually a file from the perspective of the operating system. So all you need to do is write an alternate data stream to the tracing directory, and as far as the system service is concerned, it is actually a file inside Windows, even though kind of it isn't. That's kind of cool. And all you need is file write data permissions to that directory. So any directory you can create a file in is theoretically vulnerable to this sort of attack, and who knows, you maybe find another use for that somewhere else. But of course, not everything gets fixed. So this is a bug in Win32k. They've actually had 2 goes at fixing this now, but neither of them actually fixed the UAC bypass aspect to it. So because it's not a security boundary, of course. So let's have a quick demo of that. So I've got a tool to do token manipulation. I actually demoed this in the my token talk at Black Hat, so if you've already seen that, it's probably not quite so interesting. Okay. It's not the greatest of resolutions. Hopefully it's hopefully we can see something. Okay. So the bug basically relies on you can capture an access token, and if you can instantiate a if there's like a higher privilege process running on your desktop, and it does a clipboard operation, it will actually capture that sort of token. So if I just bring up a copy in Notepad. Okay. So obviously I can type into here. You don't really need to see this at the moment. It's nothing. So I copy that, and now the clipboard has been primed. The token in the clipboard is now being captured. So in here, there's a button, Win32 clipboard token. If I click that, we can see, oops. So we've captured a primary token. We can see that it's got a high integrity level. That means it's the administrator token. You can go and look at the other stuff. But we can't actually use that directly. Even though we've got access to it, we can't really do a lot with it, you would think. But one thing we can do is we can impersonate it. But again, we can't actually just impersonate it because the integrity level is too high. But we can change the integrity level. So if we just create a new one, we can change the integrity level. So we've got, obviously, now it now runs at medium, but this is still an administrator token. And we've got like I've just got a little testing harness here, which will impersonate and try and write the file to see Windows. Okay, so it's successful, and oops. And we can just see, hopefully, see Windows test.txt. Yep. And we've got a file, hello44 gone. We bypass UAC at that point. So any clipboard operation on the desktop from a high privilege process, you can then bypass the UAC. Okay. So Microsoft almost fixed it in Windows 10. During the impersonation process, a new check was introduced and basically said, it's basically this: if the impersonation token is high, but the current process's token is not high, don't allow it. But unfortunately, this is only enabled if you change the default configuration, which is a bit of a shame. So obviously, maybe there's some compatibility issues somewhere. But the real takeaway from all this is, in my opinion, I still think the UAC settings are, by default, are wrong. Either UAC is useless, which it arguably is, because in its default configuration, any piece of malware can elevate to an administrator level. So if you're running a split token admin, there's various different ways you can get admin privileges. But if you are, the default account is always a split token admin. So probably 90% of the users out there, this is providing no actual real tangible benefit, and it's only actually providing sort of annoyance. It pops up a dialogue, and you just go, yeah, whatever, and they don't actually read it. So what's the point? Like, why maintain this sort of like pointless effort to prevent it from being exploited when it's already being exploited? And you can see that, like, there is malware out there which uses the fact that the default is wrong to exploit you. But if you really want to see quite how far Microsoft doesn't actually care about the current UAC settings, all you have to do is turn up that setting to the highest level. And this will always notify you anytime even like a Microsoft application tries to elevate. So you get stupid situations like the task manager requiring a prompt. If you are an admin user and you try and open task manager with full prompting, it's going to show you that dialogue. Thanks. Thanks very much. Like, that's not very helpful. Because it's already a solved problem. Like, Windows 7 reduced the attack surface. Part of the whole reason of UAC was to make application developers not do stupid bloody things and require admin privileges, and then Microsoft obviously don't care. Okay, sorry, that's my rant of UAC, if you didn't guess that one. Okay, Symbolic links. And I'm not going to talk too much about it. If you want to see my previous presentations on this sort of stuff, it's all out there. But the interesting thing about this is the first sort of three main symbolic links you can attack from sandboxing, sandboxed applications have been mitigated in Windows 10, which is kind of awesome. Like, mount points are now limited. You need to, if you want to create a mount point, which is like a directory symbolic link, you need to have write access to the target directory, and the target directory has to exist, which basically makes it pretty much useless from an attack perspective. You've got registry key symbolic links, and they're just banned outright. Like if you're running in a low privilege sandbox, you're not allowed to create registry symbolic links at all. And object manager symbolic links, there's some cool like feature like you can create them, but no higher privilege process will ever follow them. That's kind of cool. What's even cooler, I think, and obviously not particularly Windows 10 specific, is that this has been actually backported. I really did not expect this to be backported. I saw it in some of the preview builds of Windows 10, and I thought, wow, that's kind of awesome. And then it ended up getting backported all the way to Vista. It's like, who is this company, Microsoft? Are they going strange? Like, very strange, like changes of attitude. But of course, nothing's ever perfect, of course. So I'm not obviously going to give the details just yet. At some point in the near future, this will be fixed. But obviously, I'll have a quick demo of bypassing that mount point mitigation. OK. Let me just try and reduce the setting size. You can actually see it a bit better. No, actually, that doesn't actually help at all, does it? OK, right. OK. OK, is that all right? People see that? OK, so I can just create, say, a target directory, so target 1, and the command interpreter actually has a built-in tool, mklink, which will allow you to create a junction, a mount point. And so this obviously doesn't use any special tricks to do it. It just does the normal operation. So if I try and create mylink1, pointed at target 1, it works, obviously. But if I try and create mylink2, pointed at target 2, which does not exist, I get file not found. And even worse, if I try and point it at, say, the Windows directory, something I can't actually write to, I get access is denied because I can't open that directory for write access. So, of course, let's just use my tool. So mylink2, oops, pointing at C Windows. And you do some magic, and it seems to work. So if you do a directory listing, we now have, obviously, a junction pointing at mylink2. And obviously, we can just list that, and we get the Windows folder. So obviously, I'm not going to give any real details away about that, but hopefully, it's not too long before it gets fixed. At least less than 90 days. OK. Win32k. You gotta love Win32k. I was thinking about like what image can I represent Win32k with, and a colleague kind of sort of stick it into image search and have a look. And obviously this came up with a load of blue screens, so I had to use that at that point. It was actually like inevitable. But Win32k is renowned for its stability and its security, and it's completely perfect. Except for maybe fonts. If you saw my colleague Giroux's talk yesterday about hacking fonts in Windows, maybe you know fonts aren't great. There's one or two bugs in the font processing in the Windows kernel. So Windows 10 has actually done something about this. And actually, it's not just done one thing, it's done two things about this. So like, it's duplication of effort here. The first one is there's now a custom policy you can specify which says, I do not want to support custom fonts at all. So any fonts loaded from files or memory, I want you to just explicitly say no. Now, prior to Windows 10, you could have Win32k disable. And this just was a blanket turn off all Win32k, which sounded probably good on paper, but actually as a practical measure is very difficult to achieve because it's very difficult to remove Win32k from Windows. The other one is user mode font driver. So if you are to allow custom fonts, it's better that that bug crashes a user process instead of crashing the kernel. And so effectively gaining very little additional privileges. So this is something I started looking into for sort of the updates for Chrome. Like I implemented a simple sort of change set for implementing the font lockdown using the process policy. But I thought I'd look at the user mode font driver as well to see if there's anything interesting I can do with it. And it does run as a normal user in your user session, but it runs as an app container, so it's actually sandboxed. And that's pretty good. Like, okay, from, say, perhaps a Chrome perspective, getting into the app container sandbox probably is better than being in the Chrome sandbox, but still, it's a bit of a significant change. It was curious. When I started looking at it, initially I couldn't open the process. It's like, why can't I open this process as a normal user? It is running as a normal user. And it turns out the process itself is access control list to system only. And that seems very strange. Like, what? Why would you ACL a process to system only? What is there in this process which is so secure that you can't touch it? And now there is some previous versions apparently of the preview where this process ran as a protected process. And so obviously you got the sort of security by default. And maybe as it got ported to using sort of user mode sandboxing, a technique to do something equivalent was sort of just fashioned, basically. So I thought, okay, first, assuming there is some attack surface in there, I need to at least be able to get into that process and attack that process before I can actually realistically attack the attack surface. So this got fixed in September. I was quite surprised it got fixed, so I hadn't any inkling that it was going to be fixed. But obviously, I provided the initial bug report. So every process token, or every token on the Windows system, has something called the default DACL. Now, normally, when you say create a file, the access control list is usually inherited probably from the parent directory. So the parent directory has an ACL which says, this entry, I want you to give this entry to any created file in my directory. But not everything works that way. Not everything has inherited ACLs. Instead, for example, kernel objects usually need some sort of mechanism to determine who is allowed to access them. And it does that by taking the current token's default access control list and applying it to any kernel object. So prior to the September patch, this default DACL had entries for user, all that sort of stuff. It was all standard. After the September patch, only system can now actually, the default DACL is only for system. So why would that possibly be the case? What attack vector could you possibly use for that? Well, it turns out, obviously, threads, for example, are kernel objects. And while the initial creation of this process was making sure the process and the initial thread was system only, every other thread which got spawned in that process ended up with the default DACL. And so I can just open the default DACL, frig with its thread context, get it to jump to load library, and get it to load a library for me. And yeah, you bypass it that way. And so obviously this patch, now that all the default DACLs, you've also got owner rights, which is a trick to prevent owners from attacking it as well. And hopefully it's now secure. I'm not fully verified that yet. Okay, so we've broken into that process. We've actually got access to that process. What was it that they were trying to prevent you from doing? And the only thing I can really think of is Win32k has got some additional, effectively system calls, but they're escape calls. So you call ntgdi escape, and you can pass a particular value. It's like ioctl type thing to Win32k. And there was various different user mode font driver specific Win32k escape calls. And one particularly caught my eye, just because it has the name create file. And yeah, before the September patch, basically, it was a arbitrary file exploit. Technically, you could only write to specific files, but because it was using the ZW form of create file, and it allows you to create write access to that file, and it also gave you the handle back. It didn't create a kernel handle. You could get access to that handle, create a symbolic link, a file-level symbolic link, and then write an arbitrary file to anywhere on the file system. After the September patch, that's all gone. And basically, it's now secure. You can only do the read. Quite why you even need this, if it's going to do an access check from a app container. If you can read it, then great. If you can't read it, well, why are you even calling into the kernel for it? It seems very strange. So there might be other interesting calls I've not actually found. But this one was obviously the most obvious vulnerability in there, and you could use that to escalate your privileges. So yeah, everything's attacker control, no security check, and it's all gone. Now this, I'm basically coming up to the end, but this last sort of major bit is sort of talking about almost like the dangers of trying to do security research on pre-release versions of operating systems, or pre-release software in general. So Windows 10 has a new Windows object type called Silo. And Silo turns out to be some sort of special new container mechanism. It might be for its like Docker support. It's not entirely clear. But basically, it allows you to put a process into a silo and then do some fun stuff. And one of the fun stuff is you can actually change the root object directory. And that was allowed. So you could call create silo object and then change the root object namespace directory to something else. Because obviously you want to silo it. It's effectively like a chroot for Windows processes. Now I thought, okay, this is really awesome from a Chrome perspective. One of the things Chrome Sandbox has, which is a problem, is it's really difficult to completely prevent access to drivers. Because the driver objects are a bit special. If you just talk to the driver name itself, the kernel will enforce security. So only if there's a really, really big screw-up on the part of the driver author will that be vulnerable. But if you put a special name after the driver name, it treats it as something called an object namespace, driver namespace, and it will bypass any security checks. It's the responsibility of the driver to verify that security. Well, that's not strictly true. There is a flag you can set, but by default, you can bypass that. So it increases the attack surface. So it would be lovely to change the root object directory and prevent people ever being able to access any device whatsoever, regardless of context. But unfortunately, most kernel code does not actually expect that you can replace the object directory, and that's a bit of a security problem. For example, if a kernel code in your current process wants to open the registry, it has to pass the path /registry/machine/something. If I can replace the root object directory, I can redirect any registry call in the context of my process to any other location, and that's a problem because there are various parts of the kernel which kind of rely on that for security. Same with files, same with devices, all that sort of stuff. If you can trick it, you can do some nasty stuff. So you can see the bug issues there, number 459. You can go and have a look at my proof of concept. But sadly, before RTM, it was fixed. So silos were very much a transitional thing. And even though it kind of looked pretty concrete and pretty fixed, they disappeared and got merged into normal job objects. So all this effort of trying to find a cool exploit for this vulnerability was totally wasted. And it's a bit of a shame for like my hopes for, say, Chrome mitigation work or something like that, because it would have been a useful feature, but now it's behind a TCP check, privilege check, you can't actually access it, which is a shame. So yeah, my public service announcement for this, if you take one thing home, don't bloody security do research on beta software if there's a reasonable chance it's going to change before it gets released, because you'll be very, very sad. So this is sort of last couple of slides. These are the sort of bits of Windows 10 or Windows ecosystem that I kind of would have talked about, but not really had the time. So things like Control Flow Guard. Control Flow Guard's awesome when people aren't bypassing it, of course. And obviously it was in Windows 8.1, but it is just like the first OS where a majority of people are probably going to see it is Windows 10. Privacy options, I don't think I even have to sort of talk about that one, really. Cumulative updates are an interesting one, and just from a perspective of you never know now what security updates are being applied to your system, because they bundle up the security updates and potentially upgrades for your functionality, and you can't choose one or the other, and it can get a bit messy. And from a personal perspective, having the fact that you can't just sign drivers anymore, I think it's good probably from a security perspective to a certain degree, but not necessarily from my own perspective. If I want to write a driver to do something cool, I always have to run it in test mode, or I always have to disable driver signing. And of course, this would be great if it was considered to be a security boundary, but Microsoft have not traditionally liked to issue fixes for bugs where you can straddle between administrator and kernel, because it was not a security boundary, because you could just load a driver. But if you now have to get Microsoft to sign your arbitrary driver, I think that arguably becomes a bit more of a security boundary at that point. But we'll see what happens with that. So my conclusions, obviously, as the title of the talk was, there's definitely progress, 2 steps forward. There's definitely at least 1 step back somewhere. But there's always stuff to attack. Windows is a complex operating system. You can always find something of interest to break. So, before I go, I think it's a legal requirement that you're not actually allowed to do a talk about Windows, certainly local privilege escalation, without at least showing one local privilege escalation vulnerability, which isn't currently patched. So I'll show that. Oops, let me just restart him. Okay, so let's say the display isn't particularly ideal. Oops, okay. So I'm just going to run some generically named, you can't really see it there, run exploit, because why not? So we're running our exploit, and it'll take a few moments because it's thinking about it. It's really time-consuming and tiring exploit to run. Not really. It's just, I don't know. I haven't optimized it to actually not take all this time. Ooh. Go on, go on, go on, go on. Leaving you in suspense. Oh, hang on. It has actually popped up. There we go. So, who am I? I am NT Authority System. So, I think that counts as a privilege escalation. And that works from low as well, right? So it's also typical in these scenarios to sort of say, okay, thanks very much, and you can all bugger off. I'm not going to tell you how that works. But in this case, I'm going to be really generous to the 44-con crowd, mainly because Microsoft hasn't fixed it for 6 months, and it's been publicly available. So if you want to get local system on a Windows 10 machine, go and track down issue 222. It will work in a default installation of 7, 8, 10. Fine. I may put out the actual fully working proof of concept. This proof of concept will just write like a test file to an arbitrary location, but obviously you can repurpose that and do what you will. So that is the end of my presentation. Thank Thanks everyone for coming, and if anyone has any questions, you can either accost me now or accost me later. So thanks very much.